Okay, this is the Year 11 Physics Term 2 final revision, and your final exam was to answer the questions on pages 275 through 276 and page 284, and this covers pages 256 through 283 in the textbook. Your work is due Thursday, May 7th, 2020 at 8 p.m. You can send a Word file or a PDF file, or if you've already done it in your pink book, that's fine. Just take a picture, a clear picture of the pages, and you can send me that in Google Classroom. Okay, we're going to briefly go over the information in this Unit 5, and I will post some videos that will have some more information on the topics. It is Unit 5, Density and Pressure. It begins with the density. The equation is density equals mass in kilograms over volume in meters power 3. Remember, volume is three-dimensional, so it is meters power 3. The equation is this funny looking P, which we say rho. Rho is equal to mass over volume, or M over V. The units of density is kilogram for mass over meters power 3 for volume, not power 2, meters power 3. Or we will also see density in grams per centimeter power 3. Be sure to check for unit conversions. Some of the questions you may need to convert meters to centimeters or grams to kilograms, so read carefully. So the density of water is 1,000 kilograms per meter power 3, or 1.0 gram per centimeter power 3. So if you could imagine a cube, a box of length, height, and width, all of 1 meter, filled with water, that 1 meter cube would weigh 1,000 kilograms, or about as much as a small car. Or we can imagine a 1 centimeter cube filled with water, and that would weigh 1 gram. So every side of the cube is 1 centimeter. That weighs 1 gram. And remember that 1 milliliter is the same thing as 1 centimeter power 3. So I could have the density of water being 1 gram per milliliter. So when we talk about volume, we are talking about 3 dimensions, and the units are in meters power 3 or centimeters power 3. Some of the common shapes we will be talking about are a cube or cuboid. To find the volume, we multiply length times width times height, and they all have to be in the same unit, all meter or all centimeter, and that will give us meter power 3 or centimeter power 3. For a sphere, the equation, the volume of a sphere is equal to 4 over 3 times pi times the radius power 3. To find the volume of a ball or a sphere. To find the volume of a cylinder, that's pi r. That's not right. Sorry, pi r squared. We remember that's the area of a circle is pi r squared, pi r power 2, times the height. So you can imagine this circle and then stacking up this circle by the height. So the volume of a cylinder, pi r power 2 times the height, and the volume of a cone is, again, pi r power 2 times the height divided by 3. If they give you a question that involves volume, most likely they will give you the equation, unless it's maybe a cube or a sphere. But these are good to know. Float or sink. Objects sink if their density is higher than that of the liquid in which they are placed. So if I place something that has a higher density than water, water is 1,000 kilograms per meter power 3. If I place something with a higher density than that, it will sink into the bottom of the water. If the density is less than water, it will float. So things with a higher density will sink, and things with a lower density will float. How to find the density of irregularly shaped objects. So up here we have regularly shaped objects, and we can just, with our ruler, we can measure the sides of the container and use these equations. But what if we have something that is irregularly shaped, like a rock or something that would be difficult to measure? First, you find the mass of the object with a scale or a balance. Then find the volume by submerging the object in a partially filled measuring cylinder. And then use density is equal to mass over volume to find the density. Don't forget your units. So here we have a picture of a measuring cylinder, and I've put it on a scale, and it says it weighs 56 grams, and then I filled it to the 100 milliliter mark with water, and I see that now the mass is 156 grams. So I put in 100 grams of water, which gets me to 100 milliliters or 100 cubic centimeters of liquid. Then I place an object in the water. As I place the object in the water level will rise. So I see now, with the object placed in the water, the new volume is 172 milliliters. And the mass I see has also gone up to 209 grams. Because I couldn't find the volume of this irregularly shaped object. It would be too difficult to measure. So I just put it in the liquid. I measure the change in volume, the change in mass divided by the change in volume with the density equation. So the mass of 209 grams, and that's the mass of everything. It's the object, the water, and the beaker, minus the mass of the water and the beaker alone will give me the mass of the object over the change in volume. So I had 100 milliliters. I put the object in the water and it went up to 172. So I'm going to say 172 milliliters minus the original 100 milliliters, and that gives me 72. So that is 0.74 grams per milliliter. The density of this object is 0.74 grams per milliliter. And note that this is less than 1. The density of water is 1 gram per milliliter, or 1 gram per cubic centimeter. So actually this object would float. So if the density is less than water, for example, this example, for objects that float, weigh down the object with a heavy mass and a string to submerge it in the liquid. So what I would really need to do here is I would have to get a 10 gram or 25 gram weight and tie a string to this object so that it will sink. And by sinking, I can find the volume of the object as it sinks. But I do need to make sure that I consider the volume of the mass that I'm using as well. Pressure from solids. Pressure is equal to force over area, or this is a small p equals F force over A, and that's area, not acceleration A. So the unit of pressure is the Pascal, and we write that big P small a, and 1 Pascal is equal to 1 Newton over meter power 2, which is the area. Area is power 2. And I do need to use meters. Area must be in meters, so you have to convert if it's in centimeters or something else. Notice that decreasing the area increases the pressure. If I make this number smaller, that's going to make the pressure larger if the force is the same. So if I decrease the area in contact with the solid, the pressure is going to increase. For example, a hammer. If I bang a hammer on a table, nothing happens. I mean, I may dent the table depending on how hard I hit it. But if I use a nail has a very small area, the tip of a nail. So this area becomes much smaller, and the nail has a higher pressure. It goes right into the wood. So decreasing the area increases the pressure. And then we have pressure in fluids. This was pressure in solids. And for pressure in fluids, it's a different equation. So we have pressure in fluids is equal to the height of the fluid times the density of the fluid times gravity. Or pressure is equal to H, height, rho, density, G, gravity. H, rho, G. Pressure from the fluid is the height of the fluid above an object times the density of that fluid times the pull of gravity. So it's all the water that is above you times the density of that water times gravity. And the unit is also pascals. So we can see that if we go back to our weight equation, weight is equal to mass times gravity. If something has a mass of 10 kilograms, we multiply that by gravity, which is 10 newtons per kilogram, and we get the weight of 10 times 10 is 100 newtons. So we can rearrange this equation into gravity is equal to weight over mass. So the unit of gravity is newtons per kilogram. We also have gravity as the acceleration from gravity in meters per second power 2, but for this equation we're going to use newtons per kilogram for the gravitational field strength. Density, we already talked about, is mass over volume, or kilograms over meters power 3. So the pressure in liquids, we said it's the height times the density times gravity. So here we have pressure equals height times density times gravity. Height is in meters. Density, we said, was mass over volume, or kilograms up here, and volume, meters power 3 down here. And gravitational field strength, we said, was newtons per kilogram. So here's the newtons up here, and the kilograms are down here. So we see that this meter is going to cancel, and the meters power 3 becomes meters power 2. The kilograms both cancel, leaving me with newtons per meter power 2, which is the same pressure that we had for solids, force over area, or newtons per meter power 2 up here. So the unit is also Pascal. Pressure from a fluid does not depend on the shape or volume of the liquid, only the depth or the height of the fluid above an object. For example, pressure 3 meters down in a swimming pool is the same as 3 meters down in the ocean. It doesn't matter that the ocean is much wider, it's only dependent on the depth. And then when we talk about atmospheric pressure, the pressure from the atmosphere, atmospheric pressure is roughly equivalent to 100,000 pascals, and we also call that 1 ATM, or 1 atmosphere, at sea level. If you go up to the top of Mount Everest, it's about half of that. It also is a little bit dependent on temperature and humidity. Atmospheric pressure, 100,000 pascals. The next section talks about changes of states of matter. Changes of states of matter. And we have the states of matter are solid, liquid, and gas. In solids, the particles, the molecules, what have you, the particles are in regular, closely packed patterns. And you'll see in your book the picture of all the circles close together in a very regular square pattern and straight lines and whatnot. Liquids, particles are in a irregular, closely packed pattern, and they are able to slide past each other. So the picture of the particles in a liquid, they look kind of random, but they are still closely held, close together, although they can kind of slide past each other. If you think about a box filled with marbles, and you shake that box, the marbles will just kind of roll around each other. And in a gas, particles widely spaced and able to move about freely. So in a gas, the particles are just bouncing around the room, not held together. So now we have the changes of states. If we go from a solid to a liquid, that's called melt. If we go from a liquid to a solid, that's called freeze or solidify. Liquid to gas is boil. Gas to liquid is condense. And we can go from solid directly to gas without becoming a liquid. This is called sublimate. And the example we all know is dry ice. It goes directly from a solid block of ice to a gas without going to the liquid state. And we can have the opposite of that. Gas directly to solid is called desublimate. Excuse me. Melting and freezing is also called solidification in this book. And so we have a melting, freezing point of water is 0 degrees Celsius. The melting point or the freezing point is the temperature at which the substance changes from a solid to a liquid or a liquid to a solid. And the boiling or condensation point of water is 100 degrees Celsius. And that's the temperature at which the object or the water changes from a liquid to a gas or a gas to a liquid. And here we have a graph on the changes of states of H2O or water. So here we have temperature. This graph is in Fahrenheit. Just know that 32 degrees Fahrenheit is 0 degrees Celsius. 212 degrees Fahrenheit is 100 degrees Celsius. So this is the freezing point or melting point of ice or water, and this is the boiling point of water, or the condensation point of a gas. And then we see this direction, we are heat added. So this is increasing the heat, the amount of heat. So here we have ice, and it starts out at a temperature below 0 degrees Celsius. And as we add heat to the ice, it becomes warmer and warmer and warmer. It's still ice until it reaches the freezing melting point. And then if we continue to add heat, the ice will melt. As it melts, it stays at 0 degrees Celsius, or 32 degrees Fahrenheit. All the ice must melt before it can begin to increase in temperature. So first we have to change from a solid to a liquid, and then if we continue to add heat, the water goes from 0 degrees Celsius and gets warmer and warmer and warmer. Then we have water at 100 degrees Celsius. It begins to boil, and all the water begins to change to a gas during this boiling state change, but the temperature stays at 100 degrees Celsius until all the water has changed to a gas, and then we can increase the temperature of that gas. And notice the slope of the line. It's easier to melt ice than it is to heat water. We can see this has a very low slope, and then as we heat water, that takes it doesn't take as much energy. It's easier to melt water than to boil water. Some notes: to increase the temperature, we must add energy, heat energy, and the unit of energy is joules. To decrease the temperature, we must remove heat energy. So we could also do this graph in reverse. We could remove energy, and we would see the gas would cool. The temperature of the gas would come down to 100 degrees Celsius, and then the gas would condense into a liquid, and the temperature would remain constant. And we could remove more heat from the water, cool the water, and the temperature would come down, and then we could freeze the water. The temperature of the water as it changed to ice would stay the same, 0 degrees Celsius, and then we can cool that ice even down further into colder and colder temperatures by removing heat. During changes of state, for example, melting and boiling, the temperature remains constant until all of the substance has changed state, as we can see from that graph. Evaporation. Evaporation is a liquid to gas change. So we're talking about liquid water to steam or liquid water to gaseous water. Liquid to gas change of state that can happen at any temperature at the surface of the liquid. So in evaporation, water can evaporate at any temperature. It doesn't have to be 100 degrees Celsius. And evaporation is when the liquid particles at the surface become gas. Boiling takes place at the boiling point, or 100 degrees Celsius, and it takes place throughout the liquid. So we see bubbles forming in boiling liquids throughout the container, at the bottom, in the middle, at the top, anywhere. So evaporation happens at the surface, boiling takes place throughout, and it happens at 100 degrees Celsius. Evaporation has a cooling effect as heat energy is removed from the surface of an object. So if we sweat and there is liquid on our skin and that liquid evaporates, that liquid changes to a gas, it is pulling heat energy from our body, and that energy is transferred to the air. So when we sweat, when liquids evaporate from our skin, we feel cooler, and that's called the cooling effect. The rate of evaporation, or evaporation in terms of time, is increased with higher temperature. So evaporation happens faster at higher temperatures. Evaporation happens faster if we have a large surface area. A bowl filled with water evaporates faster than a cup filled with water because of the larger surface area. Evaporation happens faster if there's air moving across the surface of the liquid. If there's a breeze, or if you have a fan pointed at you or across the surface of the liquid will evaporate faster. Evaporation is faster if there is low humidity, and humidity is a measure of the water molecules in the air. So if there's low humidity, if there's not very much water in the air, the water will evaporate faster. The water molecules on your skin will become a gas faster if there is less water in the air, or if there's a lower humidity. Okay, I will link some videos on these topics in your Google Classroom, and please don't forget your final exam is due on Thursday, May 7th, please by 8 p.m. so I can check it. Okay, thank you and have a great day.